Hello everyone, I'm Charles Kagayu, and today I'm going to present my work entitled Design of 3D and 4D printed continuous fiber composites via an evolutionary algorithm and voxel-based finite elements. Application to natural fiber agronomists. I would like to thank TSTL for sponsoring this work and the Bristol Composite Institute for hosting this work, as well as all my supervisors, Fabrizio, Antoine, and Adam. So in this work we're going to talk about 4D printing, which is basically adding a fourth dimension to 3D printing. This fourth dimension is time. So basically in 4D printing we give enough time for 3D printed structures to transform, deform and actuate. So in this presentation only bending is going to be considered, and only with humidity stimuli. With this actuation is created by a bilayer actuation. So basically you have different orientation of fibers between the different layers. This creates different moisture expansion in the different directions and therefore bending through the thickness. You can see on the schematic 0 and 90 degrees layers of flax fiber composites, which create then a bending actuation as it's proposed in the video at the end of the slide. So in this presentation, which most work has been published in the paper with the same name, we're going to first discuss about measurement of mechanical properties, then the measurement of Hygro-expansion properties, the voxel-based model itself, how we use Timoshenko-based model in order to assess the quality of our model, and therefore, and last, how we integrated this model into an optimization loop. So in order to model the structures that we want to model, you need different properties, such as the shear and Young's modulus. And in order to do this, in a previous paper, we produced different types of specimen, plus or minus 45 degrees for shear specimen, 90 degrees for transverse specimen, and 0 degrees for longitudinal specimen. We then immerse them in different relative humidity, and we measured then the modulus that we could obtain from all these specimens, and this value and the evolution of the impact of humidity on this value are proposed in the paper cited on this slide. In this paper we also compare the value obtained to value from the literature, especially for carbon, aramid and glass composites, and we show that in terms of Young modulus, in the longitudinal Young modulus, the stiffness of our continuous flax fiber reinforced polylactic acid is equivalent to the one of continuous glass fiber composites. In terms of shear and transverse specimens, there are still work to be done in order to be able to have comparable data, but our values are very promising in terms of reinforcing 4D printed structures. So then in order to model, we need the coefficient of moisture expansion, which represents the ability of the material to deform in plane when the humidity surrounding it evolves. So in order to do this, we 3D printed small squares of about 2 centimeters in dimensions. Then we immerse these squares into different boxes at different relative humidity, and we measured the deformation with the evolution of the humidity. So we saw that there is, on the graph you can see on this slide, there is a very large expansion through the thickness, a smaller one in the width, and almost no expansion in the length of the material. In the width and the thickness direction, the value could be interpolated with a sigmoid shape function, which you can find the equation in here. And in order to model, we used the coefficient of moisture expansion between the 11% and the 98%, which corresponds to the second value starting from the left and the last value starting from the left, respectively. We wanted our structures to be anchored in a specific framework, and this framework encompasses the structures which are produced with a continuous filament which cannot be cut. They also need to be used in order to fasten optimization. So basically we want to work with a discrete number of printing parameters which could be used as input in an optimization system, and we want to be able to play easily with this parameter in order to control the entire printing path of the structures. In this present work we tested our structure for a specific leaf, and the first layer of the structure we created is inspired by the vein structures on the leaf, which is proposed on the top images of the slide, and then the second layer is basically used for perpendicular structures to the first layer,
in order to obtain as much possible as accuracy at the local level. Then from the G-code of these two layers, we extracted two different images, and from these two different images, we were able to pixelize these images in order to obtain properties for the FO model thanks to these images. So in our model overall, we have two different layers for each have a single image. From this image, we obtain, thanks to the threshold of black and white, the volume fraction for every single pixel of the structures, but also the orientation of the equation to obtain the orientation represented in the paper. And from this orientation and this fiber volume fraction, we are able to obtain the properties we need for the FEA analysis for every single pixel. So we wanted to compare the FEA model to specific tests that we would be doing. So we printed the lifts that we talked about. We run the analysis for the specific FEA model defined thanks to the system we defined previously. And then we define two different curvatures, which are going to be the two parameters that are going to be compared between the model and the experiment. These curvatures are kappa 1 and kappa 2 on this image. Kappa 1 represents the curvature at the widest point through the width of the structures, and kappa 2 is the curvature in the longest dimension, the length of the leaf. So we define a specific setup for this test. So basically we use the DIC, digital image correlation. We position two different image correlation to have a 3D deformation of the structures. We position our specimen in 98% relative humidity before having conditioning it at 11% humidity. And these two cameras were recording the position of different spectral patterns it printed on the specimen, and therefore we're able to obtain the evolution of kappa 1 and kappa 2 as defined previously for the specimen test. So we conducted these tests on 4 different specimens with the same printed geometry, mimicking a leaf. You can see on the left, so the deformation that we obtained. So we obtained the flat leaf that you can see for 11% relative humidity, and 98% relative humidity we obtained the curved ones. This deformation showed very good qualitative comparison between the model and the experiment. We obtained basically the predicted deformation. However, regarding the qualitative deformation, we don't have the exact same value, and this is due to the different things that we discuss extensively in the paper. If you're interested, I'm going to talk about two. The first one is basically the humidity. So when you measure a specimen inside a glass box at 98% relative humidity, there is drops of water that goes on the specimen and also on the box, and this perturbates slightly the measurements. And the smaller the distance, the more sensitive it is to this perturbation, and therefore the small distance that we have been measuring had a lot of variability in what we obtain as results. The other element is the coefficient of moisture expansion that depends on the distance between surrounding fibers. It varies with the distance of one fiber to another one, and therefore as we consider only a constant value for the coefficient of moisture expansion, this introduces errors in our test. We discuss also other different influence for this difference between experiment and model, and we encourage to have a look at the paper if you are interested in this information. So we wanted also to test our model on a different model, but it's more related to literature, in order to make sure that our model is capable of modeling the kind of structures that we are representing. So basically what we wanted to do is to create a new model which is based on Timoshenko equation, which is a very trusted equation in the field of 4D printing. So this graph presents all the use of 4D print of the Timoshenko equation that we could find in the literature, and this graph represents the errors that there is between the equations and the test that has been conducted in real life. This shows that most error is fairly small, and this wide use of this equation shows that people trust it a lot in terms of predicting simple deformation for simple geometries. And so we want to compare our model to these equations. So what we wanted to do is not to use only the Timochenko equations to create a new model based on Timochenko equation. It's basically to discretize the Timochenko equation for specific structures, and these specific structures is an hygromorph in which you have the passive layer has constant distance between fiber, but on the active layer you have varying distance between fiber. And in this case specifically, it increases along the length of the hygromorphs. So basically you have the G-code that you can find on the left side of the slide, and then on the transverse part you divide it into 5 different sections, you can see on the right part of the screen, and these 5 different sections have different properties, and these different properties are used in Timochenko equations, and these Timochenko equations are assembled together in order to obtain a more complex geometry equations. And we compared that kind of system to the model that we created based on the pixel images of the G-code. So here are graphs for the comparison between the Timochenko-based equation model that we've described just before and the model based on voxel that we've described in the paper. So you can see that there is very good qualitative comparison between the two. They basically actuate with the same shape. We look at different results, reasons why there is difference in terms of qualitative results between the two different structures. You can find all of them in the paper. One that I want to talk about is the corners. Basically, when you print a continuous fiber composite in which you are not capable of cutting the edge, then when you do back and forth, you will leave the little edge on the specimen, and this will have an effect in the actuation, because this material will stiffen the material in the length direction, and therefore our model is capable of accounting for it. The Timochenko beam equation is not capable of accounting for it, and this is one of the source of discussion that we consider in order to explain why there is this difference between these two models. So as I said at the beginning, one of the objectives of this project was also to try to put this kind of modeling system in an optimization loop. So we wanted to consider a genetic algorithm for our optimization. In order to do this, what we wanted to do is to create a parameterization of the entire G-code. So basically all the parameters that you see on this slide are capable of defining entirely the printing path of the structures. And then we wanted to define an interval of possibilities for all of these parameters, and using these parameters in order to optimize them to get the actuation that we wanted with our specific genetic algorithm that we considered in this modeling. So this slide defines the different steps in order to create our optimization algorithm for our structures. So we created a genetic algorithm to optimize our structures and wanted to see if we could fit our model in that kind of optimization loop. So this goes in different steps. The first one is to define the general geometry of the structures. Basically, for instance, it's a leaf that we've been discussing of this presentation. So the one inspired by veins and then the perpendicular layers. Then we defined the smaller set of SOPs, so set of parameters, for SOP stands for set of parameters, which fully describe the printing path. And then we create N1 random SOPs. So basically it's a set of different SOPs which are going to be used in the optimization structures. We run the model for every single one of these SOPs, and we calculate the optimization function for each of them. This optimization function called phi is shown on the right side of the screen. It basically compares the kappa ref I, which is the reference that we set as target in the model. So this is going to be two curvature for a specific example. The ref1 is going to be, and ref2 are going to be the different curvature that we have as objective for the leaf, so the exact same curvature that I've been describing in previous slide. And so comparing these two, we're going to be able to minimize this phi value. And so the minimum values obtained for the SOP are selected to go to the next round. The worst are deleted completely, and the rest are cross-linked, mutated like a normal genetic algorithm, and then assembled with the best one from the previous round. And there is a new set of random SOP that comes to complement this element. And we are playing on the amount of best SOP selected, worst SOP deleted, and the one which were cross-linked and mutate, in order to see how we can converge as fast as possible to a global or local parameter for our optimization. And so we ran this loop several times until we obtain a SOP that we were satisfied about, and we define a criteria to be satisfied previously to the implementation of. So I'm going to go very quickly on this graph. It's basically a convergence graph. It shows how the different curvatures are converging. So in the previous slide, there are different coefficients that you can assign for the different curvatures that you want to converge. And this will make them converge more or less quickly, the different curvature. For us, curvature 2 was the most important, so we made it converge quicker. But overall, we consider the black dots as the most important because it's full convergence of the model for the different curvature. We describe limitation on this model regarding assigning curvature which are not compatible together, and we also discuss other limitations of the models by experimenting on it, that you can define. Look in the paper. All the work that I've been describing in this presentation has been published in a paper in additive manufacturing, and with Eric Kim, Adam Perman, Antoine Ludwigou, Sofiane Gesasma, and Fabrizio Scarpa. And I hope you enjoyed this presentation. I would like to thank BCI for hosting this research, GSTL for sponsoring it, and every one of you for staying until the end of this presentation. And of course, if you have any question about everything that I've been talking about, please feel free to email me, contact me, however you can. Really happy to work on this subject and looking forward to hearing from you.